Hello everyone. Today we are going to discuss about the fixed bias circuit. So there are following DC biasing circuits. The first biasing circuit is the fixed bias circuit. Second is emitter stabilized bias circuit. Third is collector-emitter loop. Fourth is voltage divider bias circuit. And the fifth one is DC bias with voltage feedback. So all these circuits are used for the stabilizing of the Q point. So we know that the collector current IC is depending upon beta IB and the reverse leakage current ICBO. And we have discussed that if the temperature is increased, then the reverse leakage current ICO also increases, which increases the IC current. So there should be some mechanism by which we can control the increase or decrease of the collector current. So there is only one way of controlling the collector current, that is by decreasing the IB current if IC is increasing, or if IC is decreasing then IB must increase. So for that we have first biasing circuit, which is called fixed bias circuit. So in the fixed bias circuit we have the input is applied between base and emitter terminal. Output is taken from the collector emitter terminal. The resistance RB is connected to the base. Resistance RC is connected to the collector. So the base emitter is forward biased by using the biasing voltage VCC, and collector and emitter terminal are reverse biased by using the biasing value VCC. So as we are doing the DC analysis, so we have to remove the capacitors and the AC input signals. Why the capacitors are removed? As we know that frequency for the DC is equals to 0 and the impedance provided by the capacitor will be infinite. So the capacitors behave as an open circuit for the DC analysis. So after removing these all capacitors and AC input signals from the circuit, we have to do the DC analysis of this following circuit. So the circuit will be look like this. We have this VCC, this is base current RB, this is an NPN transistor, and the collector is connected to the collector resistance RC, and emitter terminal is grounded. So we have removed the capacitors. So this is your base terminal, this is emitter terminal, and this is the collector terminal. The voltage between the base and emitter is VBE, and the voltage between the collector and emitter terminal is VCE. So now for the analysis we will apply KVL on input side and output side. So step 1 is to find out the value of IB from the input side. Step 2 is to calculate the value of IC by using this relationship, that is IC is equals to beta IB. And step 3 is to calculate the value of VCE from the output side. So now we will be having this base-emitter loop, which is also called the input side. So in this input side we have this biasing voltage VCC, the resistance RB, and in this base the current is IB. So we will apply the KVL on this input side, which is VCC plus VCC minus IB RB minus VBE equals to 0. So from here IB is equals to VCC minus VBE upon RB. So this is the step 1 from where we have find out the value of IB. This is the step 1. Now step 2 is to find out the value of IC, that is equals to beta IB. So we will put this value of IB in this particular relationship, that is beta times VCC minus VBE upon RB. So this is the step 2. Now we will apply the KVL on the output side. So on the output side, again we have the biasing voltage VCC, which is making collector and emitter reverse biased. There is a resistance RC, and through this collector the collector current is IC and emitter is grounded. So we will apply the KVL. So KVL will be VCC minus ICRC minus ICRC minus VCE equals to 0. So we have to find out VCE. So VCE is equals to VCC minus ICRC. So as of now we have find out the value of IC. IC is equals to beta VCC minus VBE upon RB, and VCE is equals to VCC minus ICRC. So these are the Q points, which is VCE and IC. Now if the temperature is increased, if the temperature of this circuit is increased, then the collector current IC will also increase. We have to make some mechanism so that if this IC or there is a change in the transistor, then the value of beta will also change. So both of these are going to change the value of collector current IC. So we have only one parameter which can control the IC, that is IB. So if IC is increasing, then IB must decrease so that we can control the IC current. But if we look IB for this circuit, IB is equals to VCC minus VBE upon RB. VCC is a DC battery, which is a fixed value. RB is a resistance, which is also a fixed value, and VB is equals to 0.7 for the silicon, and it is equals to 0.3 for the germanium, which is again also fixed. So there is no such cause which can decrease the value of IB if the IC is increasing. So that's why the fixed bias circuit is the worst circuit for the amplification purpose. Now if we see the saturation current, then saturation region, so saturation region means we have this equation, that is VCC minus VCE minus ICRC equals to 0. So if VCE is equals to 0, then IC will be equals to VCC upon RC, which is the maximum current which is flowing through the fixed bias circuit when VC is equals to 0. So this is the values for the saturation region. If we see the load line on this output characteristic, so the load line must be having 2 points. The first one is the point on the y-axis. For the point on the y-axis, VCE is equals to 0. VCE is equals to 0, and we have seen that when VC is equals to 0, IC is equals to IC VCC upon RC. So this is this point, VCC upon RC. Similarly, the next point on the for the load line is on the x-axis, and for the values on the x-axis, y is equals to 0. As of IC is equals to 0, so VCE is equals to VCC. We have this equation, that is VCE minus VCE plus VCC minus IC RC equals to 0. So value of y is equals to 0. So VCE come out to be equals to VCC. So this is this point. So we have 2 points, and by using these 2 points we have make a load line on the output characteristic. So the Q is the operating point where the values of RB sets the values of IB, that sets the value of VCE and IC there. Now circuit values affects the Q point. So if we increase, that is VCC, by the values, for example here VCC1 is greater than VCC2 and VCC2 is greater than VCC3. So we have seen that this IC is equals to beta times VCC minus VBE upon RB. So if you are going to increase the value of VCC, then the value of IB is going to increase, and which is going to increase the value of IC. So this is the load line for the VCC equals to VCC1. This is the load line. This is the load line for VCC2, and this is the load line for VCC3. So you will find that the value of IC current is decreasing. Why? Because VCC1 is greater than VCC2 and VCC2 is greater than VC3. So by looking at this particular thing, the Q point is also shifting. So as of we are increasing the value of VCC, the Q point is also changing. The Q point for this load line is here. If for the value of VCC1, if we change the value to VCC2, that means we have decreased the value of VCC2, the Q point shift to this point, and we have further decreased the value of VCC, then the Q point shift to this particular region. So we are shifting from active region to the particularly saturation region there. Now we will see the effect of resistance also. So we have seen that when VCE is equals to 0, IC is equals to VCC upon RC. So if you are going to increase or decrease the value of RC, the Q point will again change. So here R3 is greater than R2 and R2 is greater than R1. So if we will put this R3 here, then the value of current will be very less, because R3 is greater than R2 and R1. So this is the point. Similarly, when we have changed the resistance from R33 to R2, where R2 is less than R3, the Q point has shifted to the load line. Y on the point on the y-axis has shifted to this point, and we have decreased it to R1. Then the point shift to this point there. So again, what we are seeing that the Q point is again changing or shifting with the changing in the values of the circuit values. So here in this example we have changed the values of collector resistance. in the previous we have changed the values of the battery, that is VCC. Now we will see that if we change on the values of IB, then what will happen. So by changing the values of IB, that is if we are taking the value of IB equals to IB1, then Q point is here. We have increased the value of I2, then Q point shifted to this point, and when we have increased it to the IB3, the Q point shifted here. So in this way the Q point is shifted by varying the different values. Thank you.